Every structure begins with a simple question: what is pushing, pulling, twisting, or accelerating it? Before calculating stress or deformation, an engineer must identify the load correctly. In this lesson, we will classify loads by direction, spatial distribution, variation with time, and rate of application, then connect each classification to the internal forces it creates. A load is an external force, an applied couple, or an imposed action acting on a body or structure. Gravity, fluid pressure, wind, contact forces, thermal restraint, and support reactions can all influence structural response. We first isolate the body with a free body diagram. External loads and reactions act on that isolated body. If we cut through it, internal axial force, shear force, bending moment, and torque become visible at the section. A longitudinal or axial load acts parallel to the member axis. Pulling away from the member produces tension, pushing inward produces compression. When the line of action passes through the centroidal axis, the loading is concentric and ideally produces direct axial stress. When the load is offset by an eccentricity E, it is equivalent to the same axial force P acting at the centroid, together with a bending moment equal to P times E. The stress is therefore no longer uniform across the section. A transverse load acts perpendicular to the longitudinal axis. On a beam, it creates shear force and bending moment, so one side tends to shorten while the opposite side tends to elongate. If the load also misses the shear center, torsion may appear. Direction alone is therefore not enough. The line of action relative to the member geometry is equally important. A concentrated or point load is an idealization in which a small contact region is represented by one force at one location. Real contact always occupies a finite area. A distributed load spreads continuously over a length, surface, or volume. A column can deliver a concentrated resultant to a footing, while the footing spreads that action into soil pressure. This is a load path. The same action changes its spatial distribution as it passes through connected components. The dimension of distribution determines the correct intensity and units. A point force is measured in newtons. A line load is force per unit length in newtons per meter. A surface traction or pressure is force per unit area in newtons per square meter, also called pascals. A body force density is force per unit volume in newtons per cubic meter. Keeping these units visible prevents a line load, pressure, and total resultant from being confused. A body load acts throughout the material volume. Self-weight is the clearest example. Every small volume contributes its mass times gravitational acceleration. In a rotating component, centrifugal inertia may also be represented as a distributed body force. Instead of drawing thousands of small forces, we use a force density and integrate it over the volume to obtain the resultant. A surface load acts through traction over an area. The traction may be normal, as with pressure, or tangential, as with shear and drag. Hydrostatic pressure increases with depth and acts normal to every submerged surface. The individual pressure forces combine into a net resultant. The upward resultant associated with this pressure field is buoyancy. It is important to remember that buoyancy originates from surface pressure, even though the final resultant is often shown as one upward arrow. A line load is distributed along a curve or length. Examples include an idealized load along a rail, the load transferred along a narrow support, or surface tension acting along a contact line. A beam carrying a uniform line load of intensity W over a length L has an equivalent resultant W times L acting through the centroid of that distribution. For a uniform load, that location is the midpoint. A static load remains constant with time. A slowly varying load may be treated as quasi-static when it changes much more slowly than the structure can vibrate. A dynamic load changes in magnitude, direction, or position rapidly enough that inertia becomes important. Wind gusts, seismic ground motion, waves, rotating imbalance, and moving vehicles are familiar examples. The distinction depends not only on the load but also on the natural time scale of the structure. Load time history explains how application rate changes response. A gradually applied load rises slowly, allowing the structure to remain close to equilibrium. A suddenly applied step load reaches its maximum almost instantly and remains there. In an ideal undamped linear system, that step can produce a peak displacement twice the corresponding static displacement. Impact loading involves contact between bodies with relative velocity, so kinetic energy is transferred during a short interaction. Shock or blast loading acts for an extremely short duration with a very high rate. Its effect is strongly related to impulse, the area under the force time curve. Equal peak forces can therefore produce very different responses. Classification becomes useful when we trace a load into the structure. Cut a loaded member and enforce equilibrium. A force normal to the cut becomes axial force. A force tangent to the cut becomes shear. A moment that bends the member becomes bending moment, and a moment about the member axis becomes torque. These internal resultants generate the stress and deformation that design calculations must control. A distributed loading can often be replaced, for equilibrium, by an equivalent resultant. Its magnitude is the area under the load intensity diagram, and its line of action passes through that area's centroid. This replacement preserves net force and moment, but it does not reproduce local contact stresses. Use the distributed model when local pressure matters, and the resultant when studying overall equilibrium. The complete mental model is now clear. First, identify direction, axial, transverse, or torsional. Next, identify distribution, point, line, surface, or volume. Then examine time dependence and application rate, static, quasi-static, dynamic, gradual, sudden, impact, or shock. Finally, follow the load path and reveal the internal forces. Correct classification is the bridge between a real physical action and a reliable engineering model.